Okay, Boker Tov. So as I thought, I'm actually getting into some sort of time pressure. I don't know, I'm going to take another hour from Noga on Wednesday, I suppose. But, then we'll see how she managed. So what I want to do today is essentially review and give you some intuition about the rest of Shannon's communication theory. Well, I know that it's called information theory, but I actually prefer to call it Shannon's theory of communication. Which is essentially the name Shannon himself gave it in his original papers. And only later on it was called information theory, but I think that information theory is more, or maybe even much more than communication theory. Although for many years they were considered the same thing, but I think that information, the concepts of information, as we already saw in this course, are usable and applicable to many other problems, which are not just the original Shannon communication model. But still, we need, and I think it's very important to understand the basic ideas and structure behind Shannon's theory, which is still the heart of, if you look at the IEEE transactions on information theory, which is the main technical journal in this field, it's still mostly about communication, models and theorems. It's a very mathematical area in the mathematical field, which makes it a little bit inaccessible to many people from different disciplines, and they actually enjoyed for many years closing it into a very specialized niche of engineering, which I think was very bad for this field. But I think it opens up, partly due to many things that related to learning and related to biology and related to many other things. And I think that this particular class or particular field of brain research is one of those places where ideas for information theory are applicable to many other problems, and I believe it's a really fundamental domain of knowledge that you all need to know a little bit about. So as I said already, I mean, the communication theory, the model of communication of Shannon was made out of those somewhat simple-minded view of communication, where you have a point-to-point communication, where we have a source, we have a receiver, or sender and receiver, and we have a channel. There's some telephone or radio open here somewhere. It's a bit disturbing. Okay, so now you know the channel, yeah. So a channel, which is essentially Shannon's abstraction of the physical media that connects somehow the source with the channel, with the receiver. And one of really Shannon's greatest insight was that very little of the physical details of the channel are really important. So essentially, the source, let's now denote the source messages as something like W's, just not to confuse. So the source is sending messages, which you can think about as words or sentences or something like this, whatever it is that I'm trying to communicate. And the receiver is supposed to get some sort of received message, which is not necessarily the same as the original message. Let's call it W hat. And the channel, which is, as I said, is this physical media, which can be, as I said, I mean, the air between us or the electromagnetic waves that go through the Ethernet, through the ether actually, whatever, and all sorts of other physical things that can carry information. I mean, it can be optics, it can be sound, it can be electronics, it can be whatever, gravitation, whatever it is that I'm actually sending the information through is essentially doesn't matter in the sense that the whole thing, the beauty and the essence of information theory is that everything is transformed into properties of distribution in some sense, of statistical distributions, and the media itself is irrelevant. Now, I was already hinting to many of you, we have a similar problem when we think about the brain, at least in my maybe not so popular view of the brain. I mean, there's a mess of neurons and biology and chemistry and electronics and whatever you want inside our brain, which is very, very complicated, and it's made out of cells and synapses and neurotransmitters and whatever you want. A lot of details, but eventually this whole box is doing something which is simpler in a way in terms of what's coming in and what's going on. So this top-down view of communication that Shannon actually introduced, actually it has this type of ideas precedes Shannon by at least 100 years or 150 years in physics, when people start to think about thermodynamics and hydrodynamics, and so this idea of top-down view of things is not entirely new and not originally. It's not the first time it happened. So it happened in science first in the 19th century when people started to think about heat engines and without really understanding the microscopic structure of matter. It happens again in Shannon's communication theory, and I believe that we should keep this type of top-down view of things when we think about the brain as well. So we have no choice. I mean, the details, the microscopic details are too complicated. Too complicated for anything to... I know that you hear different views of this from different people, and rightly so, but I personally don't believe that we can really understand the brain by a bottom-up view, completely bottom-up. When trying to understand why I behave the way I behave now by thinking about molecules in the synapses, it's just like trying to read a book with a microscope. I mean, it's not the right resolution for doing this. So we need some sort of way of thinking top-down, which is still mathematical and rigorous and useful. Okay, so as I said already, the source is characterized by distribution of messages. It's actually what we call an information source, which means it actually generates messages as a function of time, all the time. Information source. So we already know that if this is a stationary source, which means, okay, things look more or less statistically the same all the time, like my speech now. I mean, if you don't understand what I'm speaking or what I'm saying, essentially it's just some sort of noise generated with some statistics. Okay? And it sounds more or less the same all the time. And actually, it is more or less the same all the time. But so in order to actually make sense of what I'm saying, you need to dive in and decode it in some useful way. So there is some sort of an entropy source here, or entropy rate, which characterizes the source. I mean, as we already know, I mean, so the source doesn't have to be IID or even Markovian. I mean, it can be a stationary process which generates messages. Okay. Now the channel is a more tricky thing. I mean, more tricky thing in the sense that I'm really simplifying it, maybe more than I should at this point, by thinking about it as what we call memoryless. Memoryless, this is again one of those abstractions of Shannon, is assuming that there is a distribution that connects, that tells me, okay, what is the probability that if I put X into the channel, I got Y out of the channel? And when I say memoryless, it seems I'm actually thinking about a channel which has no memory, which means each symbol that comes into the channel is transferred to another symbol out, maybe in a different alphabet or in a different domain, or who knows what. I mean, I can put into the channel sound waves and get out of the channel spikes, okay? Or get out of the channel, I don't know. So they don't, X and Y don't have to be of the same nature, the same character. But when I say memoryless, I actually means that if I take a very long sequence here, so this is also going to be a function of time in some sense. So at every time step, I'm inserting into the channel xt and get out of the channel yt. And when I say memoryless, there's an assumption that there is no memory, which means that the probability of a long sequence, given a long sequence of inputs, is simply factorized. Which means each symbol is transferring through the channel independently. This is, of course, a very strong assumption, which is usually not true for physical channels. But it's approximately true. Let's say that this channel is actually, let's say, the sound, the air in the index class and the channel between my mouth and your ear. This is actually a physical system which has memory, in the sense that if I make some sound here, there is some reverberation of the sound in the room, which takes some time to decay. But if you don't have too much echoes and too much reflections here, then it's actually going to decay very quickly. And so this assumption of memoryless is not so bad for many physical systems. If I sample, or if I enter the channel sufficiently slowly, if I start to push symbols too quickly, such that the echoes or the vibration, the reverberation inside the channel are still there, and then things become much more complicated. But of course, one of my students just calculated the capacity of a channel with memory of a dynamical system with many modes of vibration that it's actually possible to do this calculation. It's not so difficult, and there's another thing. So channel with memory means that there's something in the channel that remembers the previous symbols that went through it, and creates what we call, sometimes in speech we call it co-articulation, for example, which means that one symbol is actually affecting the way the other symbol is. It's not exactly the same, but it's similar. So there's some correlation between these things. Okay, so when we say memoryless, essentially there is an assumption that whatever happens in the channel, in the physics of the channel, my symbols are sufficiently sparse or sufficiently far from each other to ignore this possible correlation between the symbols. Which means that, okay, so this is the assumption of memoryless, this independence. It makes life a lot easier. But actually, we know now, and we actually work a lot on channels which have memory, which means that let's say there's some internal state of the channel, which is actually changed every time I touch it, and whenever I touch it, it moves to another state. It's actually a dynamical system, which may change its internal state as a function of what's going on through it. So this is a channel with memory. And actually, we also talk about channels with feedback, which means that there is some feedback from the output to the input, which means that maybe I see on your eyes if you heard me or not. This is some sort of channel of feedback. Yeah. So I get some feedback from you when I transmit. Even if I don't see exactly what you understood, I get some maybe weak feedback through some sort of a sensor that actually tells me, okay, this can be a feedback. It's actually very important when you start to deal with complicated things. So feedback is some sort of information that comes back from the output to the input. And there's a lot to be said about channels with feedback. It's actually very hot and complicated topic in communications here. But again, so now we want to have the very basic results first. So we ignore feedback and we ignore memories. Okay? I think it's clear to you that in actual natural communication, both things exist and are very important. Now, so simplifying things is the key to understand what's going on, to begin to understand what's going on. And as I said already, the idea is we actually have a cost on communication. Which means usually there's some sort of, there are two things that really matter physically to any organism, let's say communication between animals or communication between computers or whatever it is. Any attempt to transfer information from one place to another place is communication. And what really matters, let's say if you are a communication engineer, or if I require some sort of communication with, let's say, internet or whatever it is, what really matters to me, I don't care about all those abstract things like entropy and information and things like this. I care about two things usually. What is it? What are they?
Bits per second.
No, bits per second are very complicated. Tell bits per second to the guy who buy a modem. Well, maybe he knows what he's talking about, but most people don't. The fundamental things. Now, bandwidth is also a very complicated thing. I mean, you know too much. Right. I want to have reliable communication, which means I want to be able to decode the messages correctly. Okay, that's the first thing. Okay, so this is actually measured in Shannon theory by some sort of distortion, as we call it. So how close are W and W hat to each other? So this can be any measure of similarity that tells me how well I'm actually decoding the message. So when I speak, I want you to understand something like 90% of the words I'm saying. It's probably not true. But that's some sort of a distortion measure. Or maybe I want you to understand the ideas even if you don't understand the word, which is another way of, or maybe I just want you to pass the test. I don't know. I mean, there are all sorts of distortion measures. So, and of course they're different. They can be measured in different ways. So there is something called a distortion. It's actually very important distortion function or distortion measure, which tells me how well my original messages were received at the receiver. Okay. Now, in the original picture of Shannon, there was no distortion, which means he actually wanted perfect recovery of the messages. This is what we call lossless or distortionless communication. But in real life, essentially everywhere when we talk about communication, there is distortion. There are some losses. It's not perfect. Okay? So this is the first thing we care about. I mean, how distorted how reliable is my communication? So there's some sort of what Shannon called fidelity criteria. It tells me how well my communication is. What is the other thing? Or the other what we call top really thing you care about. So you care about the time. You care about the rate. So okay, I can communicate very, very slowly, but maybe it will be very reliable, but I will not get anywhere. I mean, so I care about the rate of communication, which means how many messages per unit time I can transfer. So the rate. Now these things are very important. So there's a rate, and there's a distortion. Actually, the rate, it means that how many messages per unit time I can transfer. There's also, of course, when you say bit per second, that's what you actually meant. I mean, how fast I can download the movie that I want. Essentially, this is what I really care about, and things like this. So rate and reliability. But rate is actually a special form of something more general, which is the cost of communication. So essentially, I can talk about rate, but maybe actually what I really want is the cost. The cost in terms of money, or in terms of energy, or in terms of whatever it is that I actually pay for. So, when I buy communication today, I actually pay for bits per second, but in a very non-linear way. I mean, sometimes the first few bits cost me much more than the next gigabit. I mean, just establishing a line that will give me any communication is the threshold is the most expensive part, and then of course I can get some sort of bit rate for free, more or less, and then if I want much more, I need to pay more, and so on. So the cost can be a very complicated function, and it is. Actually, if you think about cost of communication in neural systems, which I hope some of you do think about. So let's say auditory communication. So there is some effort just establishing the hardware and actually a lot of effort that actually allow you to communicate. But then I get more or less for free something like, I don't know, 10 kilohertz of bandwidth in my auditory system, something like this, more or less. And below that, above that, I'm starting to pay a lot if I really want above that. So everything has to be settled with this. And what is this cost? This cost is usually, in biology, it's metabolic cost. I mean, it's how much energy I have to invest in this communication. And energy usually goes in the brain to spike trains. So what is the metabolic cost or the energy cost of one spike? Or what is the metabolic cost of establishing synapses? So these are all complicated things again. Cost and so both the cost of a certain rate, let's say, and the distortion that I can achieve, these are really the fundamental questions. These are the physical things that you really want to optimize. So when I talk about efficient communication, I usually mean the lowest possible distortion at a given cost, or the lowest possible cost at a given distortion. There's obviously some trade-off. If I want lower distortion, I probably have to pay more in most cases. If I want lower cost, I probably can pay in distortion. So this is the fundamental trade. Remember this, at the end of this class, I'll try to show you what Shannon actually did to this trade-off. So the fundamental trade-off, fundamental trade-off of communication is the cost distortion. And as I say, cost is actually related to rate, and distortion is also going to be related to rate. So I actually would like to see this function. So what is the cost as a function of the distortion? So obviously, if I want a low distortion, so distortion is bad, okay, which means I want low distortion, and cost is also bad, so I want low cost. So how do you think a trade-off like this will look in general? So low distortion is going to have high cost, and probably lower distortion is going to have low cost. So this, I expect something like this here. Okay, but this is in general a complicated function, because in order to calculate it, I need to know a lot about the physics of the cost and the physics of the distortion, and immediately I bring up all the nasty details of the system, and it's going to be very specific and so on. So the trick is really to transform this cost distortion trade-off into something which I can calculate and is more fundamental. So how to calculate this? This is essentially the problem that Shannon faced, but really formulated this way only at the end of the story in the 60s, or in 69. Now, so as I said already, there are two. The first idea of Shannon, which is really a crucial idea, is to separate the problems of. So first of all, I'll deal with the source and transfer it to something as short as I can by compressing it. And this is what we call source coding. And source coding is essentially data compression. And then I go through another phase, which is going to deal with the noise in the channel. So the channel is usually noisy, which means that what comes out is not necessarily what I put in. It's not even a one-to-one function. If it was a one-to-one function, then I don't worry too much. So maybe I transfer it from images to text, but if it's good enough for me, I mean, if I can recover the image from the text, which I really can, then it's a one-to-one function. So I don't care about one-to-one transformation. I do care about something else. So essentially, you're going to see that the channel is going to be some sort of going to depend essentially on only one thing, which is how much mutual information there is between the input and the output. But so the first really critical idea of Shannon was to separate the source coding from the channel coding. And channel coding is usually associated with what we call error correction. I know this the board start to look terrible. That's fine. So channel coding is error correction, source coding is data compression, and we already talked about data compression. So we asked already how much we can compress the source, and the nice result, or the beautiful result, is that I can compress the source in terms of bits per second up to the entropy rate of the source. This is a lower achievable bound asymptotically. Okay, that's what we showed last time. So now I want to focus on the other part, the channel coding. Now this separation of the source coding from the channel coding is of course not obvious, and it's not obvious that you actually need it. But this was the first insight of Shannon. Let's first compress and then error correct. Actually has a high price in this separation, but this is not the separation theorem or information theory. Deal with the source coding independently of the channel. And this is where you divert to go to an imaginary engineering domain, which is actually completely wrong for biological systems. I already said it. We know that this is not true. So in fact, in biology, if there is anything like coding at all, it's done together. There's what we call joint source channel coding. And it's not only done together, it's done in ways which are not allowed in Shannon's story. So in Shannon's story, the givens are the source entropy and the channel communication, the channel conditional distribution. These are given. Can't touch it. This was the laws of his game. I can do anything around it, but I can't touch these two things. Because, okay, this makes perfect sense. I mean, I cannot change the channels. Usually they are not given to me, and I don't want to change the source. But biology is playing a very different game. Biology, as we all know, had a long time to evolve, and in this time, we actually adapted the sources to the channels in a very interesting way. So, for example, our auditory acoustic communication, the speech, let's say, or the sounds that we make which we learn to use for communication at some point in our evolution, is actually very well adapted to the eardrum, to the ear physiology, such that precisely the sounds that I can modulate with my eating and breathing organs or whatever it is, I mean the mouth and something which was developed for entirely different purposes originally. Precisely the sound that I can modulate somehow with these things, I can detect with my ears. So the frequencies that I generate with my mouth are precisely or very well adapted to the frequencies I can receive with my ears, and it's not a coincidence. It can't be a coincidence because those two things were evolved together. So I'll come back to this. This is really very, very important in my opinion. How exactly those theorems of communication theory of Shannon are applicable, if they are applicable, to what we call biological communication. It's one of my favorite topics of research, and I'm really spending a lot of time on this question, but I'm not going to read you all of it. So we're going to talk now about channel coding. So the problem is I have a noisy channel, and I want somehow to wrap it with this channel coding and decoding in order to be able to overcome the noise in the channel. So what I'm going to talk about now is channel coding. In channel coding, I restrict myself to memoryless and feedbackless channels. Okay? So channel coding, as I said, is completely characterized by this one symbol. I mean, here I actually discretize things. I mean, this was again one of those key insights of Shannon. he realized that in order to communicate, we must use symbols. This was not obvious then, and it's actually not, maybe more obvious today, but it's still a very important insight. Because, for example, my sound is not discretized. My sound is a continuous sound wave that has all sorts of frequencies and amplitudes and whatever you want. And so he had this really very fundamental insight, which was originally not even sufficiently well, that both yt and xt belongs to some, I don't know, curly y, whatever, alphabet, and x belongs to some curly x, whatever, I don't know, alphabet, and these are all finite. Actually, they can be countable, finite is easy. So, there are symbols. Actually, by this simple assumption, Shannon really started what we call the digital age. Because he realized that in order to communicate, we must use discrete and well-identified objects. And actually, of course, the language discovered it a long time ago. We have words, we have vowels, we have letters, but these are all discrete objects. So we somehow use the acoustic channel to communicate them, but fundamentally these are discrete objects. Okay, so it's going to be what we call discrete memoryless channel, which means both x and y are discrete. Now, as I said, I'm using time so in a discrete way also, which means I'm transmitting something to the channel in some frequency, which is low enough to ignore the interferences between the symbols in the channel, and otherwise as high as possible. So it turns out, so what I'm going to give you now is a very high-level sketch of Shannon's ideas. To do it rigorously and carefully, you need a lot more time than I have in this course. But I think this is enough for you to really appreciate. This is enough for this course. I will be delighted to give a much more rigorous and complete information theory course. And actually, there are courses like this. But the technical difficulty of actually rigorously proving these things, which Shannon actually didn't do, it took about 10 years after Shannon's original papers until mathematicians were happy with the proofs. So you can actually find papers by some mathematicians in the 60s, rigorous proofs of Shannon's theorem. Like Hinchin, it's actually quite funny that they thought that they proved Shannon's theorem, so that I actually think that the insight of Shannon is much more important than the rigorous proof. So there's something, the key insight which I'm going to convince you in the next 10 minutes is that there's something called the capacity of the channel. And the capacity of the channel is actually a very intuitive concept to you now, which is the capacity. The word capacity is a bit has different meanings for different problems and different things. So here I'm talking about essentially the bit rate. How many bits I can transmit through the channel reliably, even if there is noise in the channel. So the capacity is simply defined now as the maximum over all the possible input distributions of the mutual information between x and y. So this is the definition. Okay? So there's already something deep in this definition. The only thing I really care about when I talk about communications from a noisy channel is the capacity of the channel, which is just the mutual information. And to remind you, the mutual information is what? And actually what I need here is that the mutual information is age of y minus age of y given x. You know that there are many ways of writing the mutual information. This is the thing we need here. So the only thing that is going to determine how many bits per second I'm going to transmit through the channel, I can transmit through the channel without errors, is this. And this is actually, so the theorem, which I'm again going to sketch very, very in a very sloppy way, but it's all right. The theorem, or it's called sometimes the second coding theorem, where the first was the one that the source can be compressed up to the entropy asymptotically, but not before, not lower than the entropy, without adding distortion. And the channel, this is called the channel coding theorem, or the noiseless, the first channel coding theorem. That's going to be an extension of both theorems, which is for any rate. So I need to define a rate of communication. So how would you define it? You already defined it. Well, the rate of communication is something you use in your internet connections all the time. What is it? Gal said bit per second. Okay, so that's what I really want. I mean, so the rate of communication is essentially how many messages per unit time I can transfer through the channel. This is the rate. So there's something very important which I need to define. So the rate, and again, I'm defining it in a very sloppy way right now. Essentially, the log of the number of messages that I can send through the channel asymptotically divided by time. So if I can send n messages in time t, so the number of different messages as a function of time, whatever message is. I mean, so remember, I'm starting from the source, and the source has words. So I can think about it as words per second, or letters per second, or sentences per second. Eventually, as you all know, it all boils down to entropy rate. So essentially, it's the number of if I take the number of messages I can send in a time interval, so this is expected to grow exponentially with time. Why? So the same reason that entropy grows exponentially with time. If I take a very long interval, the number of possible configurations combination of things that I can put there is a product of the number of things I can put in first time, second time. So it's expected to grow exponentially. Actually, this is the only thing you really care about. So this n of t, in anything which looks more or less normally, if I independently put letters in the channel and send them, so essentially it's going to be exponentially. Let's say that I could put in every time step exactly one of k words in the channel and decode them correctly, then I have k to the t possible sequences of length t. So it's going to grow exponentially with time. Okay? So it makes perfect sense to take what? Take log, yeah, of course. So take log of nt. This is going to be linear nt. Okay? Because I said that n of t is expected to grow exponentially with t. Log of nt is going to be linear nt. So if I really want to define something which is independent of time, what will do? 1 over t. Okay, so this is written in an ugly way. So it's 1 over t asymptotically. So the rate should be some sort of a limit, if t goes to infinity, of 1 over t, the log of the number of messages I can send in time t. Okay? Yes?
What exactly is the meaning of the time? We have x1, x2, right? So the time units are discrete as well. And what do you mean how many units I can send this time? This is just how many time steps you're taking, right?
No, but maybe I can send very few units. I mean, so, you're absolutely right. It's a good question. I didn't quite define it. I just added this index t, but I didn't quite say. I also say that t is discrete. So there is a physical time here somewhere. Physical time tells you, okay, do you access the channel every second? Okay. Or do you access the second every hour or every day? I mean, it's a different type of communication. So I really care, I mean, physically, I care about time, real time. I mean, I really want to know how many bits per second you can send through the channel. Okay. Now, when you send messages, if you want to send one message, okay, send one message, I don't care. The whole thing becomes interesting when you send many messages. So the whole point is that there is a source with an entropy rate, which means it generates some sort of bits per second. Entropy rate was defined already as the length divided by n, if you remember. So the entropy rate, I already used this, of a source was the limit where I can tell you now t goes to infinity of 1 over t log the probability of x1 to xt. Now, since time is discrete, this is essentially the number of time steps I sent, and this limit is divided by t, and if you think about t as time with dimensions of time, then this is a rate per unit time. Okay? So this is essentially how many symbols I generate in my source per unit time. That's the way you have to think about it. So I didn't want to get into it, but actually there is a sampling time or a frequency that you access the channel, you access your source. So when I speak now, there is some sort of bit rate in time. I mean, I'm saying, I don't know, 2 words per second, 3 words per second, 5 words per second, depends when. So it's actually quite high, the bit rate. So if you think about it, okay, there are 10,000 words that I'm using. I'm choosing one of them. There's some sort of entropy to the language, and I'm actually sending it in a channel, in this acoustic channel, in about 5 words per second, probably less than that. But so this is some sort of a rate. So the entropy rate is always essentially bits per second. This is the way we think about it. This is the entropy rate of the source. Okay, bits or nuts or whatever you take the log with, but per second, per unit time. Now, time can be second, time is anything. So there's bits per second. You can think about it, bits per channel access. If you tell me that what is the frequency you access the channel, so it's bits per channel access. Okay, this is the rate.
Why would I access the channel different amount of time per second?
No, you can't do this. I mean, because I said, I mean, there's a limit. Okay, that's precisely the point. There's a limit to the rate that you can transfer through the channel. It will be above. So okay, so you're right. I mean, this is a very good question, right? So the theorem is going to relate the capacity of the channel to the maximum rate. Okay. So there are two things. I mean, how many messages per second on average I can send through a channel, and what is this maximum rate? And the theorem is essentially that for memory, actually it's true for memoryless, but at least under those conditions, I don't want to specify them exactly. Memoryless, feedbackless, stationary channel, the rate is always bounded by the capacity. So an upper bound, so this is what you have to remember. I know it's not a theorem, but this is what it is. So a bound on the capacity, a bound on the rate that I can transmit, the rate of messages, or the whatever it is, as you already know, rate is characterized by entropy rate, or bits per second. This is really ugly. Bits per second. So essentially, the question is, what is the maximal bits per second? This is then if I measure it in bits per second, I don't care if it's words or sentences or images or whatever it is that you communicate. Frames per second in video or whatever it is. I mean, pixels per second. I don't know. You can measure many things that you can transfer through a channel. Eventually, everything is measured by bits. This was the original message of the notion of information. And the rate is measured by bits per second. And the channel, the maximum rate that you can achieve without errors. So for any r less than this, there exists a coding scheme whatever, that will for anything less than c, there exists a coding scheme that achieves this rate. Asymptotically. So it's a asymptotic theorem, just like the coding, the original theorem. I mean, in general, I cannot do it with finite time. I need to take very long blocks. Okay, so this makes the whole thing a little bit suspicion whether it's actually useful, this asymptotic thing. So first of all, so there are two. It's a tight bound in the sense that first of all, anything which can be transmitted reliably without errors, the rate must be bounded by capacity, and asymptotically I can achieve the bound, which means I can get closer and closer to C. It's actually, there's a converse theorem that tells me if I try to transmit above the capacity, there must be an error. I mean, there must be an error. The error actually is so large that anything above the capacity is going to get to essentially random signal. That's less obvious, but that's really the meaning of the theorem. I cannot correct the errors above the capacity. I can correct the errors completely. With any degree, any epsilon of error, I can correct below the capacity for any. Okay, so the ingredients of the proof, this was really a quite remarkable theorem, one of those many in this original papers in 1948, that essentially if you have noise in your channel, even very high noise, as long as there's some mutual information between the input and the output, you can still communicate with others, as if there are no noise, Because until then, everybody thought that there is noise. There was analog noise, and there's noise, let's say there's noise, you can always just amplify the noise. I mean, people had this notion of, your copy. If you remember old copiers, which are not digital, whenever you copy a page, you get some noise, and if you copy it many, many times, after exponentially fast, it's going to deteriorate to nothing. Actually, the idea was, no. In classical communication, you can transfer information from one place to another without losing anything, even if, and there is always some sort of noise in your system, even with if there is a very high noise, you can transfer it reliably. And this is really it was a very, very important insight. So error-less communication is possible even when there are noisy channels in the system. That's actually what shapes biology when you think about it. Without this, we could not do anything. I mean, without this type of result, we could not build complicated brains because there's always noise. In every synapse, there is noise. So when I transfer, let's say, information from my eye to the V5, I don't know where, deep in the brain, I go through many, many noisy channels. And the fact that I can eventually recognize you means that something has to correct this noise along the way, although every synapse is stochastic, is noisy. Okay, so that's really a fundamental result. So what's going on here? So first of all, let's take an example. An example is a standard example that you must see. It's called the binary symmetric channel, which is essentially, okay, so the alphabet, both x and y are binary, bits. And the binary, so I send 0 or 1, and I receive, so x is 0 or 1, and y is also 0 and 1. So, and I communicate 0 goes to 0, and 1 goes to 1, and if this was always true, then it's a noiseless channel, okay? But let's say that there is noise, so 0 goes to 0 only with 1 minus p probability, and so is 1 to 1, so this is why it's symmetric. And with probability p, 0 is actually transferred to 1, and 1 is actually transferred to 0. So in some sense, the conditional probability, which is a 2 of 2 on 2 matrix, is essentially 1 minus p, 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 1 minus p. Okay? This is the matrix. It's a 2 by 2 matrix, and this is the matrix communication. So this is maybe the simplest possible channel you can think of. It's a binary communication. I send a bit, and it's with 1 minus p I see 0, with probability p I see the other one. Okay, so clearly if p is 1/2, you don't expect to see anything. Okay, which is essentially it's randomly choosing the other side. There's no capacity. So what is the capacity of this binary symmetric channel? So it's actually a very simple exercise, which you can do yourself. So the capacity of the binary symmetric channel, is the maximum of I xy, and let's just calculate it. So because of the symmetry, so essentially this is the entropy of y minus the entropy of y given x. Well, the entropy of y given x you can easily calculate. It's the binary source with p and minus p. So what is the entropy? It's h of p. I mean the binary entropy of p. Yeah, so this is h of y minus what I call h2 of p. So everything is measured to log 2 in bits, And h2 of p, if you remember, this was this function that I plotted several times. 0, 1, half is the maximum, and 1 is this. This is p log p minus p log p minus 1 minus p log 1 minus p. This is the entropy, this binary entropy. Minus p log p, log 2 of p minus 1 minus p, log 2, 1 minus p, which is maximum 1 at half. Okay? So, and then what is the maximum possible age of y? I want to maximize this. H of p is given. What is the maximum entropy of y? Y is a binary variable. 1 bit. So if y is uniformly distributed, the maximum is 1 minus H of p. Let me, I usually don't know why I write the binary entropy with small h. It's a habit I got a long time ago, so it's actually, okay, so it's the same thing. Okay? Okay, so it's very simple. Where p is 1/2, I get 0, okay, as I expected. When p is not 1/2, I get something. And of course, if p is 0 or 1, doesn't matter, I get the maximum capacity, which is lossless. Even if the code is reversing my symbols, I don't care. Okay? Yes?
But hy is not dependent on px. You say that you should maximize according to px.
Right, right. But so I'm maximizing. In this case, this happens. The maximum of y will be attained where px is also maximized. So if px is 1/2, because of the symmetry, y is going to be also 1/2. Because symmetry, just symmetry argument. It must be symmetric. So because everything is symmetric. So if y is 1, if x is 1/2, 1/2, then p is 1/2, and this is the maximum. Okay. If x is not 1/2, 1/2, then of course y will not be. Actually, y will have exactly the same entropy in x in this case, and it's going to be less than the capacity. So the capacity is the maximum. So this I already maximized. Okay. Now, so this is a very simple calculation of capacity, maybe the simplest possible, and you see it's already interesting. So now, of course, I can give you a long list of some of more complicated channels. As you can see, for example, in Cover and Thomas, it will take me too long. I don't know. So in principle, the whole art of calculating capacities of channels is how to calculate this number for complicated channels. And there are many, many possible channels. I don't care. It is fun. Whenever you have the need to actually calculate the capacity of something, it's usually a long calculation, and we can do it in some cases, in some even interesting cases. But you can actually do it numerically by simply optimizing this information over the distribution. So it's a variational eternal optimization problem. Given the channel, look for the information, the distribution that's calculated. If it's not a symmetric channel, by the way, things are getting much more interesting. Okay. But I'll come to a much more interesting problem in a second. And I'm out of time completely. You should have stopped me. So the next thing is to prove channel theorems. Okay. Or at least to give you an idea why is it true.
לחשוב על משהו שהוא לא אוסף גרפים. מה שאני חושבת, אני יוצאת עכשיו, אני חושבת שאני יוצאת סתם, לא, אז אפילו פתאום, כאילו, עוד דברים. בדיוק, אני אפילו התחלתי אני פשוט רוצה לכתוב הכל, תאוצה, זה לא ציפי שלה, קוראים לתאוצה.
יש שם הרבה יותר מה שאני כמה אני יכול להגיד כאן, אבל זה
כן. למרות שבסוף לא ישוב
כל האינסייט יותר פשוט,
אבל הדירקציונלית בכיוון הזה, זה מה שאני רוצה לראות, ואני זוכרת כבר כתבתי את זה. בסוף, הדירקציונלית הגיעה לזה, וזה לדעתי, או שזה לא שם בגרף, האמת שדירקציון הזה לא כן, השתמרתי בו.
כן, שאלה טובה, שאלה באמת מאוד מעצבנת, של הזמן, אבל נחזור לשאלה נראה אותה אבל עשינו את הרעיון הזה של זמן, ברגע שדיברנו על הגבולות האלה, נכון? עכשיו רק אתה להגיד לי, תוציא, אם אני אפיל אותו ברוח, מה האורך של השרשרת של הגז של האיקס? מה אני אומר? המקור מייצר לי סימבול פר יוניט טיים.
כן, כאילו בסדר,
ואז אני שואל, אוקיי, אני חייב לחלק בפרופי ההסתברות של סדרה מאוד ארוכה, זה יורד אקספוננציאלי, אני חולק למינוס שלו, כן?
זה תרחיב דקה. יש לנו שהיה מהרגיל.
חלק בזמן, אני חולק מערכת מאוד זה כבר בחינות של
כמו זה פעם אחורה, הסוף הולך טיפה יותר רגיל.
כשאני רואה על הקיבולת, אני חושב שכמה זה שנייה יכול להיות
אז לא משמעותי הזה, כאילו
אני אעריך אותם הרבה זמן דרך אני אשרה לי כמה פרספקט כמו שבאתי זה הכל
לא היה זמן, כאילו בין זריחות חליכה וכישלון, יש לנו
לא, זה כמה ביט בשנייה, לא זאת אומרת, ביט בשנייה, הסימבול שלי באים לאיזשהו קטע, נניח אחד מילי שנייה.
כאילו,
זה לא מה שרואים. לא, זה כן רואים, כי ברגע קצת סדרה. נכון שכל זה קראתי לזה אין, ולא ראו את זה תפור לזה. לא, עכשיו, לא, זה כן עניין שלו, זה כל משהו. כאן אמרתי יש לך סדרה באופן, אבל לא אמרתי איך היא יוצאת. עכשיו אני אומר לך, זה בעצם תהליך, ואני מסתכל על עצמי. זמן אחרי זמן אחרי זמן, יש כאן מערכת דינמית שיש כאן משהו, פרוסס שמייצר סימבולים, אז הכל חי בזמן הפיזיקלי. עכשיו, נכון שאני התעלמתי ממנו, כי אמרתי, יש לי יחידת זמן שבה אני דוגן את התהליך, אז הזמן נכנס במעבר שתגיד לי מהי יחידת הזמן פיזיקלי. באותו רגע, ה-N כאן, ה-T הזה הוא זמן, ואז אני שואל פה, ה-N שזה לחלק פה בילי, וזה יהיה N. זה יהיה כמה יחידות זמן שאתה להגיד. אבל זה לא היה חפלני. זה תתי, זה הזמן הזמן בין פגימות של בין אירועים זה להביא את הזמן של זה הכל. אם ראית פעם מערכת דינמית בזמן בזמן אז זה מה שאנחנו עושים.
אני רואה אצלך להסתיים.
לא, אני לא עכשיו על הרצה. יש לך זמן אמיתי. ראית בשביל את הפנטריה בזמן אמיתי.
נראה לי שעשיתי את זה.
חוק השני של ניוטון.
כן.
בעצם ראיתי בזמן. כשאנחנו אומרים לזמן בזמן, אז אני בעצם אומר, אוקיי, אני לא רואה את הזמן אמיתי, אני רואה רק פגימות.
ואז בשורה הראשונה, כאילו, יש לזה...
מה קורה? אז אני מעביר את הזמן שלא יודעת מה זה זמן.
אבל אפשר יותר קריטי.
אז חיה
ואז ND הזה, אם אתה אתה מניח איזושהי נקנות, לא יודע מה שזה היה, פשוט הגודל של המסורת שלי זה תקציב, כי אתה...
אז באמת אומר, הכי הזה בעצם מספר פעמים ששמעתי ברור. אין, בתוך מספר המפת שהצלחתי להעביר בתוך צודק. ואני חשבתי שאני יכול לעשות את המעבר כפי שתעזרה לך, אז זה עוד כמה.
לא, העניין של לעבור מיחידות של הקומפליטי לשניות זה לא בסוף. כאילו, עקרונית, האם יש משהו ב-NP שהוא מעבר לכמה קומבינציות?
לא, לכל הכל שאני יודע, שואל אותך כל דבר, כמה ביט ששנייה אני מעביר בדיבור שלי. זאת שאלה איטית, נכון? הדיבור סיגנל פיזיקלי שחי, אם תרצה לא תרצה בזמן פיזיקלי, ומניע גללים פיזיקליים כמו האוויר בחדר. אני יכול לצייר אותו בתור איזושהי מוטציות של הזמן. נכון? דיבור. עכשיו, זאת פונקציה של הזמן, זה האמפליטודה או הלחץ באוויר, אבל שאלה כמה ביט פרספקטיב.
מבחינה טובה.
אז אני חייב לעשות איזושהי דיסקרטיזציה של הערוץ הזה. דבר שאני שואל אותך, אוקיי, אני עכשיו הולך לעשות לא זמן. עכשיו השאלה היא כמה לא זמן אני צריך בשביל לך לשחרר אותך חבר. אז יש לנו משפט הדגימה, נייקוויץ שלא נזכרתי את הבוקר. זאת אומרת שאם אני דוגם את הערוץ הזה פי 2 לרוב המפת שלו, לא זה דבר של שנייה אבל שתי שניות. לא, אז אני יכול לעקור את הסיגנל הזה לסיגנל דיסקרטי, כלומר רק יספר על הדגימות שלו כל סיגנל זמן. ואז ואני יכול גם לעשות דיסקרטיזציה של האמפליטודה עם נורא רוצה. כלומר, אני יכול להגיד לא רק שאת הזמן אני הופך לסיגנל צדדי, אלא גם את האמפליטודות אני הופך לסיגנל צדדי, נניח אני לא אותו סיגנל 6 צדדי. ואני שם שם 2-6 רמות של אמפליטודות, ואז הפכתי את זה לאלף דיסקרטי בזמן קדים, ואני טוען שהמשפט הדגימה שסיגנתי למספיק מהר, כלומר פי 2 מהתדירות המקבילה שנמצא פה, אז אני בסדר, אני יכול לשחרר את זה בדיוק של דיסקרטיזציה. וזה מה שעושים. כשאני דוגם את הדיבור במחשב, זה מה שאני עושה. אני מעביר אותו לגרף מספרים. אבל לא אחד מהם של דיוק של דיוק. נכון? באותו רגע אני אמצא, עכשיו אני שואל עדיין כמה ביטים שני הקודות. אז אני אומר לך, כן, לכאורה, כששוחרר את הדיבור שלי, אני צריך לדבור אותו ב10 קילו. שומע בעוד אבל אנחנו מעבירים את הדיבור משהו 5 קילו שלי. מעל 5 קילו אין לי יותר אנרגיה. זה אומר שאני צריך לדבור אותו ב10 קילו, זה אומר שאני שומר 10 ביט, זה קל. בכל דגימה, אז אני צריך 100,000 ביט לשנייה. בשביל לסדר את הדיבור. 100,000 ביט לשנייה זה הרבה יותר מהאנטרופיה שלי. המשפט הראשון אומר לי, לא, בעצם אפשר לראות את זה ל-100 ביט לשנייה. כאילו 1,000 ביט לשנייה. במקום 100,000 ביט לשנייה, זה 100,000 ביט לשנייה, יש כמעט לא ספציפית קומברשת של דיבור. אבל אנחנו כל הזמן מדבר במושגים האלה של ביט לשנייה. ביט זה כל העסק doesn't make sense. זה מה שאני מחליט.
יש בזה הרבה מאוד. כאילו... יש אבל רגיל הבנה הרבה יותר עמוקה של... כן,
Okay, so as usual, you ask very good questions during the break, which I would love to share with all of you, but I don't have the time for that. So, I mean, how many of you heard about the Nyquist sampling theorem? Most of you. So you know how to discretize continuous signals in principle, which means if there are something like my sound, for example, my voice, it's a continuous signal, but since it's what we call band limited, I mean it doesn't have any energy or any information above, let's say, 5 kilohertz. then I need to sample it in how much? What is the minimal frequency which will allow recovery? So this is the Nyquist frequency, which is 10 kilohertz in this case, twice the maximum frequency, or twice the bandwidth to be more precise. And so in this case, I need, in order to digitize my continuous time voice, I need to sample it in twice the maximum frequency in this case, which is 10 kilohertz, 10,000 times per second. Yes. And actually, I can discretize also the amplitude. For example, I can represent it by 10 bits, which means only 1,000 values of levels of amplitude, and that's actually a whole question how to discretize amplitude and correctly, but that's beyond the scope of what I want to say now. So in principle, in order to, I can, the bit rate of my, the naive bit rate of my voice is how much? 10,000 times 10, which is 100,000 bits per second. That's a lot. Do you know how much you can actually compress it without losing almost anything? What is the bit rate of MP3 music? You know?
41.
Well, it depends, of course. There are many ways of coding it. If you really want lousy speech coding, you can actually get all the way to kilobits per second. But this is really bad. But if you want really good high fidelity music, like something like your CD, it's actually CD is a PC, no compression at all. But if you take a CD, it's the 44 kilohertz or something like this, or 42 kilohertz. It's really a lot of oversampling. But if you take MP3 or something like this, it's actually compressed to 100 kilobits per second or something like this. Anything between 30 and 128 is usually 128 is good enough for classical music, and I can tolerate it. So actually, this is very good. So which means I reduce it by at least a factor of 10. And this is actually source compression. Actually, it's a lossy compression because I'm actually losing a little bit, but it's beyond my perceptual distortion. Okay? So I'm talking about bits per second. That's what I'm saying. So bits per second is a very important thing. We talk about video. Do you know how many bits per second it is for video? So you all know that, because you all download videos all the time. So you know really, you know exactly what is the size of the movie. So an hour movie is about 1 gigabit. That's it. Now think how much I compress it. It's huge. I mean, it's a this compression, and you still. So this is all source compression. Okay. So when we talk about rates, I actually talk about bits per second because this is really what you care about. I mean, this is how much you. And when you talk about the rate of the source, it's really how many bits per second are needed to characterize the source. And the beauty of it, I don't need to know anything else. I don't care if I think about the source as words, or as colors, or as voice, or as video, or whatever. Bits per second, that's it. It's one of those great insights that eventually I can transform everything to units of information, or information per time. Okay, now the rate. So this is what we mean by the rate of the source, and this is what I also mean by the rate of my receiver. So if I send messages, as I hopefully convince you, even if time is discretized, the number of possible messages should be exponential in the time, because I can reuse the thing more or less independently every time step, and therefore the log of it is linear in time, and one of it is a number which I call the rate. Okay, that's very important. Now, the point of Shannon's channel coding theorem is that there is a limit to the rate that you can send through a noisy channel without losing information. And this limit is the channel capacity. And this channel capacity is nicely given by our familiar mutual information maximized over the distribution of the source. It's very clean, very nice. Yes?
In the binary example, so how can you ever send that like the binary method like that without losing information? Because there's always confusion.
Yeah, you're asking a very intuitive question, but that's exactly the miracle or the beauty of this result. So it seems that you're always losing something, huh? So how can I overcome this noise? So that was exactly the intuition and the belief of people until 1948. And that any noise is unrecoverable in some sense. No. Okay, so let me try to convince you. So the point is that there exists a code. Now, what Shannon did is a step of non-trivial assumptions that made him. First of all, he said, okay, for any epsilon greater than 0, I'm willing to, let's see if there exists a code to get the error to less than epsilon. And then, so first of all, there is a finite error. Of course, there's always a finite probability of error. Maybe I was so unlucky and that all the time, although it's only p probability, I got a very, very long mismatches. Okay, that's what we call a non-typical case. Okay, so you see that. So of course, in order for the channel to be so bad that I will get very, very long sequences of errors, then I have to be unlucky. What do I mean unlucky? It's exactly like the unlucky sample. I mean, I can sample any variable and see a bad sample. So whatever I do, I have to put the probability of a bad sample somewhere. So I cannot really perfectly guarantee it, not always, but with high probability I'm going to guarantee it. Okay, so it's going to be a probabilistic result. Now, the key to this result is the notion of typical sequences, which I already mentioned. I hope you all remember. This is unreadable anyway. So. Okay, so the key to the proof, and I'm not cheating too much when I say that, is this notion of typical sequences. You remember typicality? So remember that there was something I call asymptotic equipartition. When I talk about very long sequences, they become more and more similar in the sense that most sequences are going to behave like a typical sequence, and this typical sequence have a very clear probability, 2 to the minus n times the entropy. So this was the notion of the typical sequence. And the whole beauty of this approach is that when I take long sequences, long enough, almost everything is typical. Remember this? Okay. So here is the idea of the proof, which as far as I'm concerned is the only thing you have to remember. So let's take a very long sequence of inputs to the channel, which is going to generate a very long sequence of outputs. And I denote by this circle the set of typical sequences of length n. Okay, so these are typical. So what do you know about the number of such sequences? So these are only typical xn. I'm going to ignore the non-typical. So I tell that's the whole point of the asymptotic equipartition theorem. The probability is uniform in this set. It's all equal to 2 to the minus nh, and the number is actually 2 to the nh. Okay, so equally likely. Okay, so the size of this set is 2 to the nh of x. So here I assume, I don't even need to assume that they are IID, if I think about it as the entropy rate of the source. Okay? Not the entropy of one symbol, the entropy rate of the source. If it's IID, then it's the entropy of one symbol. Okay? Now, so typical sequences, there are only 2 to the nh sequences here for any n. It's growing exponentially with n, of course, but it's growing with the rate which is determined by the entropy. Okay? So now I look at the y's on the other side. For the same reason, how many typical sequences of y's are there? Altogether. This is also typical. So there are 2 to the nh, I want to write it here because I need this space. 2 to the nhy. It's actually 2 to the nhy. This is the total number of sequences I'm going to see. Okay? Now there is noise in the channel, which means that for every sequence here, start here. So this is one particular sequence in this set. There is noise. So there is some p to the y over x here that blows this. Okay, so one sequence is not going to be received as one sequence. It's going to receive as a cloud of possible sequences with all the noise. Sometimes this bit is changed, sometimes the other bit is changed. So there are going to be many, many sequences on the other side that are going to be received from this particular one. So there's a cloud here, which I'm going to denote by this. This is my lousy drawing. So the noise is going to blow the number of sequences that are going to send to the other side. Okay? Because now, if of course there's complete noise, which means no capacity, this cloud is actually going to be the whole thing. And it's going to blow it to anything possible. But if there is some information, which means some capacity, some finite capacity, then this is not going to be so bad. So what is going to be the size of this cloud?
It doesn't have to blow it into something that's typical. Most of the sequences are going to be typical, but some aren't.
Yeah, that's exactly. So here you are right, but the beauty of this notion of typicality is that everything is eventually going to be typical. So let's say that these are typical maps of this particular x-hen. So which means that the y-hen here have a probability Pyn conditioned on this particular x-hen. So I don't know if the notation is right. This is big Y and this is small x. So I'm taking one x here and I'm looking into what is it going to be blown into on the other side of the channel. So obviously because of the noise, it's going to be blown. It's going to be noisy. So adding random noise or adding something like it's random in the sense that every bit has some probability of being flipped, or every symbol has a probability of being mixed with another symbol. So there's going to be a cloud here. But if I think only about typical clouds in some sense, this is completely characterized by the what? By the conditional entropy. So the size of this cloud is typically n to the h y given x. But if I average over all clouds, it's actually given big X. But this is a bit tricky to convince you, but that essentially doesn't really matter. Because that's really the whole beauty of this notion of typicality. All of them are equally likely and all of them are essentially the same. So whatever happens in one of them happens to any one of them. Now, so this is going to be blown up to a smaller cloud of this typical size. So this is the typical size of the noisy version of my transmission. Okay. So the real question is, how many such typical clouds I can really pack into the typical sequences of Y without overlapping them? So overlapping them means that I'm going to confuse things. Okay. So the whole beauty of the basic intuition here, so I'm going to put many, many clouds like this. As long as they don't overlap, I'm fine. Okay? Right? Because eventually I need to decode my sequence. So I need to know where it came from. So if I make sure that this is going to map only to things here, and another one is going to be mapped only to things here, let's say, and so on, and these things don't overlap, then in principle all I need to see is where is it in this region, and I can decode my original message. So as long as these clouds don't overlap, I will have no error in my decoding. Essentially I blow it to a noisy version, but these noisy versions are very, very well restricted by those little clouds. Okay, so how many clouds like this I can pack at most? 2 to the n hy over 2 to the n hy. Also, so the number of such clouds, the number of such non-overlapping clouds, noisy clouds, is precisely 2 to the n hy divided by 2 to the n hy given x. Okay? This is the size of one cloud, and the whole area is 2 to the n h. The fact that I'm actually counting it in terms of entropy, or in terms of number of possible sequences, this is precisely what allows me to really divide. I mean, I'm asking, this is the volume, the total volume. This is the volume of one typical blared cloud. How many, at most, I can pack there without overlap? this number. And what is this number? It's 2 to the n I xy. Nice. Okay. So that's exactly why this is so important, that you remember this. Remember this. Okay. So the number of such non-overlapping clouds is at most. I mean, I can use less, but if I want to pack it as much as I can without overlaps, this is the maximum number of such blurred clouds. So notice that in principle, what I do here is I said, okay, with very small probability, which is going to be negligible in the large n limit, I'm going to get a non-typical transmission, which means this is going to get out of this one. If this happens, I'm unlucky. Okay. So when I got out of this little cloud of 2 to the n h over y over x, then I'm going to miss. Okay, I'm going to make an error. But the beauty of the typicality argument is that when n goes to infinity, when n is large enough, the probability of a non-typical transmission like this goes to 0. So this is how I can reduce the error below any epsilon. If you got this, you got the essence of the theorem. The rest are just technical details, which are too technical for me to do it. And for you, you can read it, of course, in Cover. It takes several pages in Cover to actually prove it rigorously, but it can be done. Essentially, that's the argument. I just have to do it carefully. So what do I mean? Okay, I really have to bound the probability of being non-typical and make sure that if I do it many, many times, I'm not going to ruin my code. But essentially, that's it. I'm using typical sequences, and I'm packing spheres of typical explosions or typical blurs like this. And as long as this is finite, as this is not 0, if I can have a few of them here, and the number that I can do here is precisely that, and asymptotically. So essentially, this is the number of possible spheres, which means that the number of different messages that I can send in with n symbols is precisely, which are decodable uniquely, which means no error, are precisely the number of such clouds that I can pack. So each cloud is going to assign to a message of length n. So what is the rate? It's the log of this number divided by n, which is the time. So if this is the number of messages of a distinguishable message, sequences in xn. So the rate is precisely the log of this, which is 1 over n, the log of 2 to the n I, which is, the rate is bounded by this. And maybe using this, as long as this is the case, which is exactly I, log 2. As long as r is less than I, which is, again, bounded by C. C is the maximum possible I. So I see a nice set of inequalities. The number of, the rate is bounded by this, and this is bounded by this, and asymptotically, I proved that one part of the theorem. Yes?
People are taking a code which is,
binary code, yeah.
And we are adding a Gaussian noise to every bit. You can say that.
So Gaussian noise and binary don't mix so well. So you have to somehow transfer it to real valued things. And sorry? BSC. Yeah, right.
Then there is a problem that because every signal can be mapped to every other signal on the whiteboard, right? Because every bit can change to another. What I'm generally saying that is there a truncation of the mapping in the perspective of the y? I would say that P of y is a big. You want that to be bigger than some sort of a threshold?
No. I mean, you're going the wrong direction. I mean, it's a natural intuition, but I was exactly trying to point you in another way. So I'm saying, okay, so this is really the key trick here, the key insight. I'm restricting myself to typical sequences. And I'm restricting myself to typical blow-ups of one. So you're right. I mean, this is a long sequence of bits. Let's say for the binary case, this is n bits. And Pn of them, on average, in a typical sequence, are going to be clipped randomly. Okay? So what I'm saying, okay, so it's like taking n bits, and with probability p, I flip every one of them, which means that this is going to be blown, or typically, to all the sequences which are only, on average, what we call Hamming distance Pn from the original sequence. Okay? So the error is not going to be infinite in general. It's going to be very clearly centered around Pn. So typical sequences are going to have exactly or close enough to Pn flips. That's exactly the notion of typicality. So the cases where you actually miss more than Pn are very rare, or less than Pn are also very rare. So on average, in a typical sequence, exactly Pn flips are going to occur. And that's exactly the notion of typicality. I mean, I'm centering my distribution exactly again around this. So I know that Pn here are wrong. So all I need is to make sure that I somehow wrap my words in a way that will allow me to correct on average Pn mistakes. Now, notice that what I proved here is completely non-constructive. I didn't tell you how to build the code. This is what we call an information theoretic bound. It's just like all the other information theoretic bounds that we saw already. Just like, on sorting, on whatever. It's giving you can't do on average less than that, better than that. Now I have to actually give you a constructive coding scheme which will achieve this bound. That's much harder. But of course, you can think of many ways. For example, if I know that on average only one bit is going to be flipped, then I can use, let's say, parity code. For example, I can add another bit, which is just the XOR of all the bits in my message. This is called parity check. And I know that the probability that 2 bits will be flipped is very small. So if I had enough parity bits, like this, I can verify that my sequence is correct or incorrect. And if it's incorrect, which I can verify with the parity check, or the checksum error, as they call it in some cases, I can know, okay, this is a wrong, this has an error in it. Send it again. Okay? So I send again exactly its probability Pn more than I should. And this is just going to be a slight blow up of my data. So the ideas of all these error correcting codes is precisely that. Add redundancy to the code, which means makes the bit not, so one of them, for example, is XOR of all the other, which means it depends on all the other. Or you can add some very complicated functions for the others. I mean, so error correcting code is the art of finding those syndrome functions, which are, it's an art. It's a lot of beautiful mathematics come into it, all sorts of number theory and things like this. What is the least number of equations or bits that I should add in order to actually being to identify my error? And there are all sorts of really crazy, beautiful ideas of how to do it. None of them is, by the way, used by biology probably, because not the way we do it in anything like the brain. But in principle, it's a very elegant branch of mathematics, error correcting code, which tells you, okay, so what is the shortest possible way of identifying the errors? In order to do this, I need some sort of extra bits. I need some sort of redundancy. So essentially, I take the original sequence and I add something to it. And this something is an extra bit, like parity bits, or things like this, which will allow me to decode or to either identify that there was an error and then resend it, or actually finding where the bits, where are the errors by all sorts of funny, very clever tricks. Yes?
Don't we have some probability distribution, though, over the other spheres for the probability of X given Y, even if it's like very small, but there is some probability that...
Yeah, but this probability goes to 0 with large n. That's exactly the notion of typicality. So I know that the probability of being non-typical here, so finding something here or here or here, that actually should be here, is diminishing, going exponentially small to 0 with n. That's exactly the power of beauty of this notion of typical sequences. And I know it wasn't clear the first time I said it, but now maybe it makes more sense. So it's really very much relying on this notion of symptotically typical sequences. Now, of course, okay, so this looks like a very non-constructive, and whether we can actually do it in practice, it's a very interesting question, and it's a whole branch, as I said, of mathematics. Those of you who really want to know more about it should take a course in error correcting codes. There are some experts in Jerusalem, like Alex Ramodzinsky and others, that really do this every day for their life. So you're welcome to ask them if you want, but this is not what I want to teach you. Just notice that there are very simple error correcting codes. For example, I can simply repeat every bit 3 times, and then take the majority. This is it's a very funny code, because I simply tripled the length of my sequence, but it's not 0. So instead of sending n bits, I'm sending 1/3 of n bits. But then the probability of having actually 3 errors in a row, or actually even 2 errors in a row, is very small, because I'm talking about typical sequences. So the majority of every 3 will give me the right bit with very high probability. So that's a very stupid error correcting code. There are more interesting codes called Hamming codes, which really add equations, essentially, or parity codes. Just the beginning of a very interesting field, but it's actually not so important. Yes?
The number you just gave about the correcting code?
I didn't get a single word. Say it again?
Okay, and the number you just gave is not exactly the term we talked about, because we talked about like mapping y to something which is not overlapping. And here you discuss a way to just say this is a wrong sequence. We don't care if we have overlap, we have opportunities to get there. We'll just send the message again. And when we talk about a way to map y to map x to something which is not overlapping, then it's much harder, because when we map x to different y, we change the probability of y, we change the entropy of y. So we... But multiplying by 3
I'm not sure about your question, but essentially I used everything that I know here. So I know that this is transmitted through this channel, which means that every x has a probability, some probability of getting it to y, and I'm characterizing these typical sequences by this sphere. Now, yeah.
saying that there is mapping is something that is one sequence. Then we should actually map x, and when we map x to some certain y, we change the probability of seeing this y according to the probability of the x.
That's right. That's absolutely true.
So we change the, which we...
Okay, so how can I get to the full entropy of y? Yeah, you're right. That's exactly why I need to. There's a. So far, I just said that it's bounded by the information, and then I said, okay, so let's look for a nice encoding of x. This will achieve the capacity, which actually means that this will maximize the probability of the entropy of y. But that's exactly why there is another step here, which is maximizing over all the probabilities of x. Okay, this one. But this will take care of what is just certain, this maximization. So this is the best I can do. How to actually find this particular p of x, which will maximize the capacity? This is sometimes what we call the capacity achieving prior, or the capacity achieving input. It's actually not a trivial question in general. And I couldn't decipher this question, this sentence, I'm sorry. There's too much either noise or convoluted thinking in the way that I couldn't follow. So, no, so I'm sorry, anybody can get the question? I don't understand what they're saying.
Okay, so when you add bit, which is error correcting bit, it's not a typical sequence any longer. It's a different method.
That's absolutely right. I mean, I'm adding bits which are now some sort of, call it syndrome or redundancy or whatever. So I'm adding some very specific bits. As you said, this is not going to be typical anymore.
Yeah. So this is a different method.
It's not a different method. It is the method. I mean, in order to actually being able to use this particular capacity, I'm losing some rate. I'm using some rate by adding some extra bit. Now, this extra bit, as you correctly said, are generally not independent. Actually, couldn't be independent. They couldn't be random. But if I do it correctly, they will look to the channel as random bits. I mean, so for example, for memoryless channel, the probability of flipping the code, the error corrected bits and the bits itself are exactly the same. So the error correction should be such that it can also correct the error correction. And that's exactly where the cleverness comes into the game. So I should be able to have enough equations here to identify errors, not only in the original method, but also in the correction. You're absolutely right. But that's exactly why it's not trivial, not in general trivial, to find good error correcting codes. As I said, I mean, this is a whole branch of highly non-trivial mathematics, how to do it, but it can be done. And what Shannon proof is is asymptotic, and it's not constructive. And it actually tells us that a random code asymptotically will be good enough. Look, I really need to run because I want to talk about the dual of it. Okay, so this is the essence, or at least the basic intuition about channel coding. And as I said, it's a very non-intuitive result, and all I want you is to remember this picture. Now, eventually, there's another side to this story, a dual problem. And this is the ray distortion problem. So first of all, if you look again at the communication model, I said that there is usually a cost on the channel and transmission. If you think about, again, neural communication, there's a cost in energy, there's a cost in time, there may be all sorts of costs. So what would you do if actually the capacity has a cost constraint? Okay, so let's say there's an energy constraint. So if there is a cost constraint, so which means that the capacity now is a function of my cost. So let's say actually the natural example, which I usually give more time to it, but we are out of time, the Gaussian channel. So the Gaussian channel is a real valued channel where the noise is just adding Gaussian noise. So this is a very specific channel where x and y is simply x plus some noise. And these are real valued variables. And if the noise, this C, is distributed normally, let's say with some standard deviation, with some variance, then both x and y are now Gaussian. Let's say that x was originally Gaussian and y is also a Gaussian. If I added noise, actually a wider Gaussian. Now in this case, the noise is simply increase the variance of my transmission, but what matters here in real valued signals like this, and this is just I'm just touching something which is the whole course, and is the energy of the signal. So the energy of the transmission is really very, very important. Actually, it's not the energy, it's the signal-to-noise ratio. So the higher the energy, the better I am, in some sense. But actually, what really matters is what was the variance of the signal compared to the variance of the noise. So for the Gaussian channel, this is essentially the one-dimensional Gaussian channel. You can talk about multi-dimensional Gaussian channels. This could be a very nice lecture to discuss it here, but what you should know is that the capacity is a function of the energy, and it actually goes like half log 1 plus the signal-to-noise ratio. So the energy here is the magnitude of the signal. So this is a very important formula, which was proved in Shannon, one of his first papers. I'm not sure if it was in the original paper. This is the Gaussian channel. This is actually not so easy, not so hard to prove, but I don't have the time for it. It's again based on sphere packing. I simply calculate the size of these spheres in the Gaussian case, and I ask myself how many spheres like this I can pack in a very big Gaussian, and I get this very important formula, the 1 plus signal-to-noise ratio. So this is a calculation which is done in Cover and done many other places. This is the capacity of the Gaussian channel. And in this case, you see that the higher the signal-to-noise, signal is that magnitude of this x, or the variance of x, and n is the variance of, so this is usually sigma square.
And what do you call energy?
And energy is the square, so it's a wave, let's say, and so the magnitude square of the wave is the energy. Okay? So this is just like a harmonic oscillator or something like this. I don't want to push the physics knowledge too far, but so it's the energy in the sense of sum of squares of amplitudes. Okay? So, and this is also, so this is the energy of the signal. You can call it also E or S, it's the same thing. So you see here that the capacity is a function of the energy or the signal to noise ratio. For high noise, I need to send a lot of energy, or actually, and everything depends on the signal to noise. So this is actually really a very important formula, and it's called Shannon's formula for the capacity of Gaussian channel. And it's an example where you see that the capacity in this case is a function of the error of the noise, so as a function of the energy, is some sort of a logarithmic function. So C is essentially log of, as I say, 1 over S to N, or 1 over E to N. Okay? Or 1 over E over sigma squared if you want it, which is again S to N. The notion signal to noise ratio is really very important. Okay, it's the ratio of the energy in the signal over the energy of the noise. So after the BCS, which is the trivial example, this is the most important capacity calculation in information theory. What happens in... It's a Gauss-Markov process, yeah, right. But, okay, I don't want to get into mathematical detail. I'll be happy to do it offline. Now, so this is an example where you see that when you increase energy, you increase the capacity, but it doesn't grow so far. I mean, it grows only logarithmically. I mean, okay, for small noise, this is actually linear, almost linear. It starts almost linearly. For small signal to noise ratio, because the log of 1 plus x is the first term in the Taylor expansion is x, but linear in x. But then it starts to go down, and eventually it grows very slowly. So you see that adding a lot of energy doesn't pay. You don't gain much below a certain. The improvement in the signal to noise ratio is only logarithmic. This actually is an important message. I don't need to. It's a waste of energy in terms of capacity to send very, very strong signals. Right? Blasting your ears here with energy of my speakers is not a very good idea. Anyway, but it's not going to help in terms of communication because they're getting. Okay, so there is some sort of optimal signal to noise ratio where you really want to be. So this capacity cost calculation is very typical. So in general, in order to solve this problem, I'm solving an optimization problem called the capacity cost, which is essentially I then, or the capacity as a function of E, is the maximum over I over the P excess, but such that the cost, the energy cost constraint, which is essentially usually some sort of expectation, so linear constraint, is less than some E. So this is a problem, a generalized problem, which is, for example, solved here. How is the capacity as a function of cost? And this is an optimization problem that I can actually always solve, because as you know, or as you should know, because I mentioned it already, if I think about it as a function of two functions, p of x and p of y given x, so when I think about it as a function of two functions like this, it's convex in the first argument and it's concave in the second one. Which means that it's convex in this. It's actually, sorry, it's concave in this. Concave in this and convex in this. This is something I think we showed you to you as an exercise. If not, just test it, check it. It's based on the convexity of the DKL, which I think we showed you as an exercise. So this is interesting. So it has a maximum in terms of this variable, and this is this maximum. So this is my maximum is unique. It's subject to a linear constraint like this. So this is a convex constraint, and this is a linear convex optimization problem, a concave optimization problem. So it has a maximum. This is just like maximum entropy, the same type of argument. It's concave, it has a maximum. So this is why this problem is actually solvable, and always gives me such a unique function. Actually, there's a nice algorithm for solving it. It's called it's a special case of what we call the Blout or Emoto algorithm. It's an alternating algorithm which actually solves this problem. So there's a way of finding the capacity achieving distribution, P of x, which will maximize this distribution subject to any linear constraint. So this is one problem. The other one is the rate distortion problem. Oh, I'm again out of time.
You mean that the mass of this is quantum because this couldn't be quantum because it's not quantum.
Why not? So when I say that it's concave, it means that I of some alpha p1 plus 1 minus alpha p2 for any given py given x, so the channel is given. This has a maximum, which means this is the function is larger than alpha I p1 py given x plus 1 minus alpha I p2.
What do you mean countable convex? You mean the mutual information or mean the max?
Maximum, this is what it means. No, the mutual information itself is convex, is concave in these two arguments. What is not clear here? So there are two different functions here. One is the prior over x. The other one is the channel. The channel is fixed for this problem. What I'm saying is that this particular function as a function of this only obeys this inequality. Which means it's concave. It's above the strings. Okay? Just like entropy. Entropy was also concave in this sense. Okay? So which means that there is a unique maximum to this optimization problem. Okay? Is the maximum information subject to this additional linear constraint. Okay? So I'm out of time. Not surprisingly, because I really wanted to put too much in. So I'm going to continue on Wednesday with the dual part of the story, which is the rate distortion function. So the rate distortion function is it looks completely different problem. One of them is maximizing capacity subject to cost, and the other one is actually minimizing rate subject to distortion. Turns out to be exactly dual, in the sense that one is maximizing information subject to this, and the other one is minimizing information subject to this. And this is going to give us what we know as the rate distortion function, and it's actually going to give a very beautiful answer to the cost distortion trade-off in terms of information. And that's really the highlight of Shannon's theory. I'm going to take the first hour of Wednesday to talk about it, and then the last week, it's 1 or 2 lectures that we have. I think it's the last week of the course. I'm going to give you really a crash review of Park theory. It's really doing it very wrong. I mean, I really wish I could talk more about it, but the minimum that I think that everybody here should know is just probably a little bit of the computation running theory.